Today is all about using relationships that we already know exist and helping us kind of work through some trig identities. So hopefully you checked your grade, everything looks good. If you have any questions, you can stop in and see me during my office hours, or just get those things turned in. We're going to start with doing, it's kind of a combination of two sections. I like to call this day one instead of A, but we're doing 5.1 and 5.2, and we're dealing with trig identities. I think of today as kind of like a big puzzle, and our goal is to put the pieces together to make sure that we understand kind of what's going on. So, let me get everybody in. Okay, so we're going to start here, and it's up to you if you want to. I'm actually going to tell you guys to take a screenshot of this because we have these in our notes from before. However, the big question is have you memorized these? Okay, and the first piece is our big goal today, by the way, is going to try to turn everything into sine and cosines. So what does that mean? If I have secant, I'm going to replace secant today with 1 over cosine. If I have cosecant, I'm going to replace it with 1 over sine. Now, if I have tangent, I understand that tangent is 1 over cotangent, but more importantly, tangent is sine over cosine. So I'm just going to highlight the ones that I think are the ones that you will use most often. So when you see cosecant, we want to think 1 over sine. When you say secant, it's 1 over cosine. Now when we see tangent or cotangent, we want to go to the other identities where it's already written in terms of sine and cosine. So tangent today can be replaced with sine over cosine, and cotangent is the reciprocal of that. So we're really getting into the reciprocal identities, all right? These 4 highlighted ones are the ones that I think you really have to focus on, okay? And maybe, I don't know if it helps, but highlighting these as well. Okay, notice everything that I have highlighted here can be rewritten just in terms of sine and cosine, and that's our goal today. So maybe take a screenshot of this or really quickly write down the 4 highlighted pieces, because those are our puzzle pieces, right? That's what we're going to use today. And it might take a while for you guys to get really comfortable with this. My goal today is to model a couple problems and then have you try some. So hopefully this will go as intended. Okay, like I said, I will post these notes so you can come back and get these, but if you didn't do so, take a screenshot of this right now because we're going to move on. And you'll want to have these just available to you. We are going to develop one other identity that's really, really helpful. And I hope you really make a strong connection to this one. So definitely write this page right here. I'll give you a second to copy this down. Okay, let's set this Pythagorean identity up. And it's exactly what you think it is. Pythagorean identity. Well, that's going to deal with the Pythagorean theorem. So we're going to just base this off of, and it doesn't matter if you say a squared plus b squared equals c squared. I know in geometry, a lot of times we put the c squared on this side. Doesn't matter, but let's think about what that means in the context of this setup. We know that any point that isn't on the quadrantial angles, so any point on the unit circle, will form a right triangle. And the hypotenuse is always 1. Well, in this case, we go over a certain x value, but remember, x is cosine, so we're going to call the x value cosine, and then the y value is always how high we go. So then the vertical movement up is going to be sine, the sine of the angle theta. And then again, we know the hypotenuse is 1. So knowing that I've got 2 sides of a right triangle, a squared plus b squared has to equal the hypotenuse squared. So what we're going to do is we're going to put this in here. I want it to be blue. And I'm going to call cosine theta. Now I'm going to introduce one thing quickly. So I think this is really important because in calculus, my students get confused by this fairly often. So the two sides squared, and then the hypotenuse is 1. So this is our identity. However, what I want to show you is the notation. See how this is cosine theta and then we square it? You can also write this, and it is more commonly written as cosine squared and then theta. And this is just a notation piece. And then we know 1 squared is 1. So this theorem right here, or identity, is what we're going to call the Pythagorean identity. So anytime you see cosine squared plus sine squared, or it could be flipped around, right? Because addition you can add in any direction. So it could say sine squared plus cosine squared, but that has to equal 1. That is a very, very helpful Pythagorean identity, which reduces things. If you see cosine squared plus sine squared, you can replace it with 1. Okay? Now, just like we did in algebra, we can move terms over to the left and the right, and we have alternate forms. Maybe I'll draw an arrow here. That's the Pythagorean identity. But you have alternate forms that are still acceptable. So think of this. What if I wanted to move the sine over here? So if I subtract sine squared, we also have cosine squared theta is on the left side, and then we just subtract it over, so 1 minus sine squared is equal to cosine. That is another type of Pythagorean identity. I don't like to memorize these alternate forms. It's nice to know that they exist, because if you know this one, then algebraically you can just move things over. Right? Or what if I keep sine on this side and I subtract cosine? So sine squared theta is equal to 1 minus cosine squared theta. And then, I mean, we could get a little more crazy with this. What if I times everything by -1? Right? If I multiplied both sides by -1, you could change the sine value, and that would work as well. I'm not going to get too crazy into the algebraic manipulations. Excuse me. I just want you to know that the alternate forms do exist. So if you see a cosine squared, you can replace it with 1 minus sine squared. Or if you see a sine squared, today you can replace it with 1 minus cosine squared. All right, so I'm thinking with the items that we had on the last page, the reciprocal identities, and these items here, that's everything we need today to do our work. So think of these highlighted pieces that we had on this page and this page as the puzzle pieces. Okay? I need to use those pieces to help simplify. And what I'm going to do is I'm going to do some here, and then I'm going to have you do some. Which I don't want to, I want to do these ones a little faster just so you can see it. And then basically I'm thinking these as your notes. And I'll give you a minute or two to do it, and then we'll go over it. So watch what happens here. By the way, what is our goal? Our goal is to turn everything, if possible, it's not always possible, everything into a sine or a cosine. Okay? And maybe I'll put sine of x because all of these are with x's, but notice it could be a u or a theta. So turn everything into sine of x or cosine of x. That's the goal. All right. Now what do I have? I have cosine times tangent. I'm okay with cosine exactly the way it is. But tangent, all right, well, what am I going to do? I'm going to go back to this page, and I know tangent is the exact same thing as sine over cosine. We introduced that last unit. So I'm going to replace, and that's substitution. Tangent is sine of x over cosine of x. And now you'll notice why we had you do the 5.0 homework. Now we're multiplying fractions. So you have to know how to multiply fractions. And one of the options is we're multiplying straight across. But when I do that, I have a cosine on top and a cosine on bottom. And they reduce out. And the only thing that's left over is sine of x over 1, which we're just going to write as sine of x. So cosine times tangent is really the same thing as the sine function. All right, so let me show you this one now. Now you have options here, and I don't really care how you do it, but at some point this sine has to be multiplied into each piece. So maybe I want to distribute that sine first. So I get sine times tangent plus sine of x times cotangent. Well, now it's really the same thing we have up here, right? I've got tangent. I know what tangent is equal to. I know what tangent is equal to. So I'm going to replace tangent with the same thing I replaced tangent here, sine over cosine. And then this sine originally, that was right here, that's going to stay. But I'm going to think of that as sine over 1, and those are being multiplied together. And then I have sine of x times cotangent. And cotangent is the reciprocal of tangent. So if tangent is sine over cosine, then cotangent is cosine over sine. And again, this is over 1, and they're multiplying. So now I'm going to try to simplify as much as I can. And you're going to see it's not always the same way it was before. But look at here. I've got a sine on top and a sine on bottom. So all that's left over here is cosine. I've got cosine divided by 1, which is just cosine. But now nothing cancels out, but I have sine times sine. Wait a minute. Sine times sine is squared over, on the bottom, I've got 1 times cosine, which is cosine. Now here's the tricky spot, and there's more than one way to do this, and that's why this stuff is not easy. It takes a while. But I've got a cosine over 1 plus a sine squared of cosine. And by the way, it's kind of like when you did proofs in geometry. There's more than one way to actually solve a problem like this. So I just want you to know the way that I approach one of these problems is not always the only way. It's usually what I think is best, but it's not guaranteed to be the only way to do it. Okay, so what do I have? I've got a fraction plus a fraction. Well, what do I need? I need the same denominator if I'm going to add those together. So this one needs a cosine to be added together, so I'm going to multiply by cosine. And then I've got sine squared plus cosine times cosine is cosine squared. And then notice they're each going to have their own cosine, so I'm going to replace just a single denominator. Remember, when we add fractions, they keep the denominator the same, but you add the numerators. And then, look at what happens. Sine squared plus cosine squared. That was our new Pythagorean identity that we just talked about. So we're going to replace this with 1 over cosine. And if you want to make a little note, this is the, Pythagorean identity. And then we know, and I should be very careful, I kind of don't want to use equal signs because this isn't an equation. This is just a simplifying expression. But now, what is 1 over cosine? And that goes right back to right here, which one is 1 over cosine? It's secant. So all that work turned 1 over cosine into secant of x. So I took this very long expression and used the identities and got all the way to secant. All right? So unfortunately, each one is kind of unique in its own right, so it takes a while to become really good at this. I'd like you to try some of these. The last one's a little bit more crazy, but not as crazy as this one, I think. So we've got cotangent times tangent. Remember our goal. Our goal is to turn everything into sine and cosine first. Okay, so why don't you try those? I'm going to give you, let's say, about 4 minutes on this. So notice we've got cotangent and tangent. Now, if you notice one thing right away, if you understand that these are reciprocals, they will undo each other, you automatically know what your answer is. Right? Your answer is 1. However, if you don't know that, then we're going to jump right into, okay, well, cotangent is cosine of x over sine of x, right? And then tangent is the reciprocal of that, so it's sine of x over cosine of x. And based off of our properties of fractions, we'd multiply straight across, but we'd know if there's a common factor on top and on bottom, it reduces down to 1. Same thing with sine and sine. Now, when everything reduces, remember, there's always a factor of 1 over 1. So I think it's important to note that this is 1 over 1, which we're going to actually call 1. So your answer is 1. All right, now let's do cotangent of u. Now notice, u, sometimes they call this a dummy variable, meaning it doesn't matter if it's x, u, it could be theta even. So we're going to go ahead and just do that same work. So now I know cotangent is cosine over sine. Oops. And you can see I accidentally put a u or an x there out of habit. And then we're going to multiply that by the original sine. And I think of this as sine over 1. And then notice you've got common factors on top and on bottom. You've got a sine on top, sine on bottom. That reduces out. And notice I'm doing what I said we probably shouldn't. It's not that big of a deal. I'm left with cosine over 1, which officially is just cosine of u. And the one thing I just kind of noted, I'm using equal signs. Really, in calculus, they would prefer that you use arrows. And the only reason why is equal signs kind of usually are reserved for equations. It's such a subtle thing that it is equivalent. These expressions are equal. So if you put them, it's fine. There's nothing wrong with that. All right, let's look at the big one here. The nice thing here is we've already got sine x, cosine x. Then we got tangent. I'm going to replace tangent with what tangent is equal to, which is sine over cosine. But then I've got secant. Well, and I hinted at this last time we learned it. If I spell secant backwards, this abbreviation, it looks like cosine. Not identical, but it's the same as 1 over cosine. And then cosecant is the reciprocal of sine. So that's going to be 1 over sine. And then remember, all of these need to be fractions. And now we're just going to say, okay, well, what do I have on top and on bottom? I've got 1 sine on top here and 1 sine on top or on bottom there. So they're going to reduce out. I've got a cosine on top and a cosine on bottom. And then what's left over is technically 1 times sine, so sine of x, and cosine. Well, wait a minute. Isn't sine over cosine just tangent? So the overall answer here is tangent. So notice what we're doing here, just really quick. Our goal is to turn everything into sine and cosine. So we do that, but then when we get our final answer, like this one down here, I had 1 over cosine. If that's a identity, then we would write that as secant. Or here, everything reduced out and is left with sine over cosine, but we know that can be better written as tangent. All right, so we're going to try a couple more of these just to really get the hang of it. And some of them are a little trickier. So same thing. Watch how I do this one, and then we'll see how you approach it. Now again, there's more than one way to write this. So if you see some way that you like better than what I'm showing, go ahead and do it. Here's what I noticed right away. 1 minus sine squared. Well, wait a minute. I'm going to jump back here really quick. My hint was I had a 1 and a sine squared, but they're on the same side. And it was 1 minus sine squared. Well, 1 minus sine squared is actually the same thing as cosine squared. So we're going to use the alternate form of the Pythagorean identity to do cosine squared. So I'm going to replace this whole top part, becomes cosine squared. All right, so the top part, let's do that in green. That becomes cosine squared. Now, I'm going to show more than I need. If you realize what I'm doing, you might be able to save a step. But then I've got cotangent. And we know what the reciprocal of cotangent is. That is cosine of x over sine of x. Now notice, I have a cosine divided by a fraction. I do not like to divide by fractions. So we're going to change this to multiplying by the reciprocal. So instead of cosine over sine, it's going to flip. And it's going to be sine over cosine. And then now I have a fraction times a fraction. Okay. And you might notice there is a cosine factor. I've got a cosine bottom and I have 2 up top. Remember what this means. This means cosine times cosine. So I'm going to get rid of the squared and turn that into a 1. So then what's left over is cosine x on top times sine x. And we don't have a theorem or a factor that gives us exactly that. Like the best possible form to write this is just cosine times sine. And that's as far as we can go. So I'd like you to try it with this one. And I'll just give you a small little hint. It's very similar to the first step we did up here. And usually that's the hardest thing for students to recognize. So go ahead and try that one. We'll give you about a minute. If you are watching this video, hopefully you're going to hit pause and try the your turn problems on your own. One thing that I kind of just jumped into and assumed you guys recognize this, but here's the way my brain works, is I know that cosine squared of theta plus sine squared of theta always equals to 1. That's the one Pythagorean identity that I have memorized. And then I notice anytime I see a 1 and a cosine squared, I'm thinking, can I algebraically manipulate this to get it to look like this? So this is saying, can I get the cosine over here? So it belongs with the 1. And now it's a perfect representation of sine squared. So that's the first step, is we're going to replace the top with sine squared theta. And then the bottom stays. Now, this, we don't have to do anything tricky because I'm not dividing by a fraction like I did over here. But I've got a sine up on top. I've got a sine squared on top and a sine squared on bottom. Some students like to do this. I would do this part in my head. But I just do want you to understand, what does sine squared mean? It means we have sine times sine up top. And that just might help you visualize why we can reduce out. If I have a sine on bottom and it's squared up top, we could just go ahead and reduce it here and say, well, what's left over is just a sine theta Or if you don't like that, then you would have to do this step and say, well, here's my sine factors reducing out, and what's left over then is just sine. So this overall item reduces down to sine of theta. And again, you will get better at this with practice. That's kind of why we're doing a good amount of these. All right, now we're going to take a look at some proving. So I would maybe write down this part in red, and then I'm going to do these two, and then you will work on this goal here. But you'll notice now we have an equal sign. So our goal is this, the directions are prove the following identity. So I want to prove that secant squared theta equals cosine squared, or secant squared theta times cosine squared theta is equal to 1. So I want to make the left side look like the right side. Okay, so watch how I do this one. And hopefully you'll kind of see how this goes. Now I am going to do or introduce some notation that maybe takes an extra step, but it's an important thought process. The first thing is if I have this written as secant squared theta, remember that's the same thing as secant theta and then squaring. Same thing here. This is cosine theta then squared equals 1. Now, I don't want to move anything to the left and the right. We're going to keep the right side as is. Okay, always keep the right side, don't change it. Don't move anything over here. So what does that mean? I'm going to just replace what I know about secant. Okay? Well, what is secant? Secant is the same as 1 over cosine, and then the squared would be out top. But I know that if I'm squaring a fraction, I'm really going to square the numerator and the denominator. And notice how I snuck this 2 instead of writing it as cosine like this. I snuck it in there. And then this didn't help me, so I'm just going to rewrite it. But notice what we have. This is the same as cosine squared over 1. And it should always equal 1. So I'm doing my best to make the left side look like the right side. And what happens? Well, I've got a cosine squared on the bottom and a cosine squared on top. Those are going to go away. What's left over is 1 squared, which is just 1 over 1. I want to keep my colors the same so we can just see that. So I get 1 over 1. And that equals 1. So I usually do this, and then I put a little smiley face there because I showed the left side turned into 1. So the left side equals the right side. All right? Now, let me show you this one before you guys move on. My goal now is to prove that cosine squared minus 1 over cosine is equal to negative tangent of sine. So I want to make the left side look like the right side. And my hint is always deal with the left side. Okay? That's usually the way these problems are set up. I think I very rarely have seen one where you deal with the right side. So always do the left side and make that look like the right side. Well, notice what I have right here. I've got a cosine squared and I got a minus 1. That's kind of interesting because what I know is that cosine squared plus sine squared is equal to 1. But if I subtract this, if I subtract the cosine over, okay, we showed that before. If I subtract the cosine over, that's not, I have a negative cosine and I have a positive one. I have the opposite of that. So what we can do then is you can actually take and multiply both sides by a negative 1. Okay? Algebraically, that makes sense as long as I do the same thing to both sides. So this is another type of algebraic manipulation. So then I have minus 1 plus cosine squared of x And really, if I wanted to make it look exactly like that, what if I just put the cosine first and then I subtract the. Right now, that's not the only way you could do this. You could bring the sine, originally, you could bring the sine over here and bring the -1 over here, and you get the same thing. But what did I just show? I had just algebraically manipulated the one fact that we knew, cosine squared, and I made it turn into cosine squared minus 1 can be rewritten as negative sine squared. So I'm going to rewrite this part as negative sine squared of x over cosine of x. Now again, my goal is to make it look like this whole right side. And nothing really jumps out at me. And this is one of the things that just is a little bit tricky. Remember what we can do with the sine. Another way to think of sine squared is sine times sine. Now notice it's not negative times negative because that would be a positive. So I just put the negative out in front and I attached it to this one. And then this is cosine. Now notice I can put cosine times 1. And when I multiply fractions, you just multiplied straight across. So I'm in my head I'm thinking every move that I make, if I undid that, does it give me back where I started? So here, sine times sine would give me sine squared, and it's negative. Cosine times 1 is still cosine of x. So I didn't do anything incorrect. But what I did do was I rewrote this. And now I've got sine over cosine, which is really just tangent. Okay? And then that negative is going to drop down. And then I've got sine of x over 1, which is just sine of x. And notice what I did? I made that look like my goal. My goal is to make the left side turn into the right side. It's not easy, right? This is not easy. It takes a while. Okay? So I want you guys to try this one. And we'll give you a couple of minutes to work. Okay, let's go over these. I'm going to kind of try to show you some shortcuts here that might help. So what I'm going to do is I'm going to replace tangent with sine over cosine. Okay, so I might even cross that out. I know that tangent is sine over cosine, and I know that cotangent is cosine over sine. Right? So I'm kind of thinking of those in that place. And then if I distribute, maybe this isn't the best thing to do to show you guys shortcuts right now, but I need to times both sides by cosine. So I'm distributing the cosine. And it doesn't matter which way I write it, in terms of which one, if I want to write cosine and then sine or sine and cosine. But then I'm going to notice these are all technically over 1. And I got a cosine on top and a cosine on bottom here, so this will reduce out to just sine of x, which is the first part that we wanted. And then I've got a sine on top and a sine on bottom, and those are going to reduce out. And technically what's left over then is a cosine of x times a cosine of x. And those are being multiplied. So a better way to write that is cosine of x squared. And notice we got the left side to look exactly like the right side. Okay? All right. I want to show you this one, just another quick identity one. I don't think you need to write it, but there's something helpful that can really make this one a lot friendlier. And it's just a little bit trickier. one of the things you can do is notice when you have two pieces being added together, because it's addition, if you look on both sides of those equal signs, what do they have in common? They have a tangent. And this gives evidence to why we practice all the work we did before. I can factor out a tangent of x. So that's what I'm going to do. I'm going to put a tangent of x on the outside. And then what's left over is sine squared plus cosine squared. And then you'll notice that sine squared plus cosine squared is equal to 1. Right? That's my trig identity. It doesn't matter if sine or cosine is, as long as they're both positive, sine squared plus cosine squared or cosine squared plus sine squared, they're both equal to 1, so all that's left over is tangent on the left side is equal to tangent on the right side, and we're done. But the key on this one was I noticed there was a common factor that I could pull out. So it's like the reverse distributive property. All right. Let me show you this one. This one's a little bit tricky as well. And you might notice, ooh, I've got a sine squared and a cosine squared, but it's not plus. And that's one of the big things here that's just a little bit tricky. So I notice on the right side I've got a cosine squared, and I kind of want to keep this cosine squared here as possible. So I want to deal with the sine squared. And I know that if I algebraically manipulate, you don't have to write this every time, but you could do it in your head. Okay, what can I get that will replace sine squared? Well, what if I move this cosine back over here? I know that sine squared can be replaced by with 1 minus cosine squared. And then I used x, but really we're using alpha. And then we're going to subtract cosine squared of alpha. Okay. Well, now, if I've got 1 cosine squared alpha minus another cosine squared alpha, that's subtracting 2 of the same thing. And now look, I've got the left side exactly equal to the right side. Okay. All right, and then this one, nothing crazy, but how can tangent over sine turn into secant? Well, tangent is the same as sine of theta over cosine of theta, but then I'm dividing by sine of theta, which I'm going to turn that into a sine theta over 1, because that tells me I'm dividing fractions, which means I'm going to change this to multiply by the reciprocal. And then you can see you got a sine on top and sine on bottom. And I'm left with 1 over cosine, but 1 over cosine is secant. And the left side equals the right side, so we're happy. Okay. All right, I want to see, we've got one last thing to talk about. Why don't you guys try this one? Go ahead and give this a shot. It's a little bit of a tricky one, but we'll go a couple minutes on it, and then we've got one more slide after this. It's tough. This is a challenge. But here's the way I would approach it. So what I'm going to look at is I know that cosecant, I want to change this into terms of sine and cosine, but cosecant is the same as 1 over sine. Right? And then if I square the top, and square the bottom, that becomes 1 squared, which is 1, over sine squared. And then I'm subtracting 1. Now here's the interesting part, and it takes experience to kind of know how to do this, but I need to subtract, and I'm going to rewrite 1 as sine over sine. So notice that sine divided by sine is 1. But the reason why I did that is so I can get the same denominator, and it's almost the same denominator. And since I'm writing this myself, instead of making it sine, let's say sine squared over sine squared, right? Sine squared over sine squared is still 1, but now I have the same denominator. And what this turns into then is 1 minus sine squared up top, and we're going to keep the denominator the same. And then you might notice a very special identity here. 1 minus sine squared is the same as cosine squared. So I actually end up with cosine squared of x over cosine squared of x. Over sine squared of x. Well, cosine over sine is cotangent, and then the fact that they're both squared proves that cotangent squared is equal to cotangent squared. Okay. Now, I do want to mention, because I just checked Delta Math, and I saw 2 people were completely done with this. And I want you to know that if you're only focused on getting the Delta Math homework done and that's it, I don't know if that's enough practice for you. So if you're not paying attention to the notes that we're doing here today, we're covering more than what's in the Delta Math. And it's making me nervous that you won't be well prepared for the stuff coming up next year in calculus, if you're only focused on just getting the Delta Math done and that's it. So please be cautious of that. All right, these are our last 2 examples, and they're pretty quick, but they look very tricky. So our goal is to write each expression in factored form. Okay, now what we mean by that is we got to factor it. Okay? Factor this expression. Well, notice this is cosine squared plus 2 cosine of x plus 1. I've got a cosine and a cosine. Well, what if it wasn't cosine and cosine? What if it was x squared plus 2x plus 1? And actually, I got a little bit of a better way to show you that is a little bit more calculus related. So how about this? What if we let u equal cosine of x? All right. Now, what I'm going to do is, if there's a cosine, I'm going to replace it with u. So this cosine squared is really u squared plus 2 times cosine, well, that's 2u plus 1. I could have used x, but since I already have cosine of x, I wanted to pick a different variable. But notice, we're just basically doing u substitution, which is a method I'll teach in calculus on next week, by the way. Well, what are we going to do now? We did u substitution. The only reason why we did that was to make it just look easier for us. And now we're just going to factor. And you could use the box with the circle in it if you want, but I think you can do this in your head. What are factors of positive 1 that add up to give me 2? I know I'll have a u here and a u here. Well, what times what gives me 1 but adds up to give me a positive 2? That's u plus 1 times u plus 1. And since it's the exact same thing, we're going to write that as u squared. Okay, so this is just simplifying. And then the last piece is we know what u is. Right? We went up here and said, wait a minute, u is actually cosine. So cosine of x plus 1 squared. That is what this original expression factors down to. And then because our original problem was terms and cosines, we had to bring it back here and now rewrite it so the final answer was with cosines. We just replaced u with cosine, and there we go. Now, I'm not saying you have to do u substitution, because you might be able to see that you can factor out a cosine times a cosine and a 1 and a 1 and get the same thing. This is just a skill that is definitely helpful later on in calculus. All right, last one, we'll do this one together because it's tricky as well. It says, write each expression in factored form. And you'll notice you've got a constant term, you have a sine, and then you've got another cosine mixed in here. And if we're going to take the factoring approach like we did on the first one, they have to have the same values, cosine and cosine, okay, or cosine squared and cosine. I can't have a cosine squared and a sine because those aren't like terms, so I can't factor them out. Well, hopefully you're seeing this part right here and you're thinking, oh, wait a minute. I know what 1 minus cosine is. So we're actually just going to replace that to start. Use a different color. So I'm going to replace the fact that I know 1 minus cosine is really sine squared. Okay, that was our Pythagorean identity. Just replace that. And then, I don't love the way this is written for me visually. I always like to have the sine squared first. You do not have to do this, but I think it's beneficial, because I want to rewrite this. And now we're going to let u equal sine of x. Okay, that's my u substitution, because if you can't see how this is factored, if we rewrite it as u squared minus 2u plus 1, now we can factor it. So I'm thinking, okay, I know how I got the u squared. That was u times u. Plus 1, how did I get the plus 1, but it had to add up to negative 2? That's negative 1 and negative 1. And you could always recheck. If you FOIL this out, you should get back to where you started. And then I know that those are the same thing. And the last step is replace u with what we said it was equal to. In this case, is sine. So I want that in red. And there you go. Now, you might wonder why we're doing this. Eventually, we're going to set this equal to a number, and we're going to actually be able to solve and find x. So there's a reason why all of this is setting up for what we're doing, and why do we use identities, why do we try to factor it, and so on. Okay, so that's what we got. We basically did two things today. We used trig identities to simplify expressions, and we factored expressions. And my hint is do the u substitution if you can't see it originally. Replace whatever trig function is with a variable, and that'll help you solve it better. All right, tonight we got 5.1 and 5.2 day 1 on Delta Math. Make sure you submit a screenshot to Schoology. If you need any help, I'll be available in my office hours from 1 to 2. Have a great weekend, and remember, next week we do not have school on Monday, and the hours got flipped. So Tuesday next week is hours 2, 4, 6. So I won't see you next week until Thursday in person but we will have something for you to do on Wednesday, February 17th. All right, so just please know the schedule. Adios. Have a great weekend. We'll see ya.